Welcome to This Explainer. Today, we are totally cutting through all that overwhelming buzzword hype to actually look under the hood of artificial intelligence. We're going to examine the foundational concepts and see exactly how these algorithms process information to make really high-stakes decisions in live electronic markets. Let's dive in. I absolutely love the analogy our source material uses to frame this. Think about how we learn as humans. You wouldn't teach a child what a sports car is by handing them a massive spreadsheet of rules about engine torque and aerodynamics, right? No way. You just show them a few examples, and their brain naturally connects the dots. Well, machine learning essentially attempts to replicate that exact same process. So, here is our roadmap for today. First, decoding the buzzwords. Second, how machines actually learn. Third, deep learning architectures. And finally, real-world AI challenges.
Let's kick things off with Section 1, Decoding the Buzzwords, or as I like to call it, the Matryoshka doll of AI.
Seriously, think of these concepts just like a set of Russian nesting dolls. Artificial intelligence is that biggest, outermost doll. It's essentially any technique that mimics human behavior. Open it up, and inside you find machine learning, which is all about iteratively learning from data. Drill down another layer, and you've got artificial neural networks, which are mathematically inspired by actual biological brain synapses. And finally, nestled right there at the very core is deep learning, utilizing deeply nested layers for highly advanced feature learning. Now, the contrast here is super striking. See, shallow machine learning algorithms, they're great for low-dimensional data, and they're highly interpretable. But they force human engineers to manually design and extract the features. It's tedious. Deep learning, on the other hand, does all that heavy lifting automatically from massive, raw, high-dimensional data. But there's a catch. The trade-off is that it operates as a complex, practically untraceable black box. All right, let's move right along to Section 2, how machines actually learn, focusing on the assembly line. This is basically the evolutionary tale of programming. We started out with traditional, explicit programming, where humans literally handcrafted the entire model. Then, shallow machine learning came along, automating the model building, sure, but still requiring that manual feature engineering. And then, finally, deep learning enters the picture, combining feature extraction and model building into one incredibly powerful, automated end-to-end pipeline. So, every modern machine learning system progresses through 4 specific stages. First up, ingesting raw data input. Second, extracting features to preserve the really important discriminative information and drop all the useless noise. Third, building the model to identify patterns. And finally, assessment. This one is absolutely crucial. You have to test the model on out-of-sample data to ensure it hasn't just blindly memorized the training set.
Moving to Section 3, Deep Learning Architectures, let's look at the roster.
This quick roster summarizes the primary architectures available to developers today. Just like in construction, you absolutely have to pick the right tool for your specific material. You wouldn't use a hammer on a screw? Similarly, you choose a CNN for image data, an RNN for sequential or time series data, again for generating new content, and autoencoders if you're dealing with dimensionality reduction or anomaly detection. Let's actually look a little closer at a few of these. First up are convolutional neural networks, or CNNs. These are the undisputed kings of computer vision. They are specifically designed for data with spatial relationships, like the pixels in an image. What makes them so powerful is their hierarchical learning. So the first few layers of the network might just learn to detect basic edges and corners. But as that data moves deeper into the network, those edges are incrementally aggregated into complex shapes until the final layers can confidently recognize a house, an animal, or a car. It's amazing. Conversely, we have recurrent neural networks, or RNNs. Now, RNNs don't care at all about the spatial layout of pixels. They are totally obsessed with sequence and time. Their architecture features internal feedback loops, which essentially form a rudimentary memory. This allows them to remember early inputs while they're processing later ones, making them absolutely perfect for predicting volatile stock markets. We're doing natural language translation, where the context of a single word completely depends on the words that came before it. Then we have GANs, or Generative Adversarial Neural Networks, which are utterly fascinating. A GAN actually consists of 2 competing networks locked in a non-cooperative zero-sum game. You have a generator network trying to create realistic fake data and a discriminator network trying to catch the fakes. They literally train each other until the generator is so good it produces incredibly realistic novel content. I mean, they can invent totally new art and music. However, they also pose massive societal threats by generating highly deceptive deepfakes meant to manipulate public opinion or even markets.
Okay, let's wrap up with section 4, real-world AI challenges, where we really need to ground the hype. Because, as it turns out, an algorithm that achieves 99.9% accuracy in a sterile, perfect lab might fail spectacularly in a real, messy business environment. Implementing these intelligent systems means overcoming 4 major hurdles: managing the delicate triangle of architecture, parameters, and data, combating bias and drift, dealing with black box unpredictability, and navigating strict resource limits. Think about it. The data we feed these models is heavily generated by humans, which means human cognitive bias easily infects the training data. A prime example highlighted in our source is Amazon's infamous AI recruiting software. It accidentally learned to discriminate against women because it inherited historical biases hidden deep within its dataset. Furthermore, even if your model is perfectly unbiased today, it might completely fail tomorrow due to something called concept drift. This happens when the real-world variables literally change, like, say, a new competitor entering the market, making the historical data the model trained on completely obsolete. And because deep learning acts as a highly complex black box, it is terrifyingly unpredictable outside of its training data. This makes it highly vulnerable to adversarial attacks. The researchers note a totally fascinating example where something as simple as putting a strategically designed sticker on a stop sign can completely trick an autonomous vehicle's vision system into seeing a speed limit sign instead. Yikes. Because of this, there is a massive push right now for explainable AI, or XAI, to augment these models so human operators can actually audit exactly why the algorithm made a specific choice.
Finally, building deep learning models from scratch requires enormous computational resources. To avoid these astronomical costs, many businesses use transfer learning, basically taking a massive pre-trained model and just fine-tuning it for their specific task. This has given rise to a booming market for AI as a service. But while buying off-the-shelf AI saves time and money, it carries severe risks. Companies might accidentally import models infected with biases, or much worse, models containing hidden backdoors and classification triggers deliberately poisoned by malicious actors.
Which leaves us with a final, really provocative thought to ponder as we close out this explainer. As the ecosystem for AI as a service totally explodes and businesses race to integrate deep learning into their workflows, how can we possibly rely on these outsourced black box brains for high-stakes decisions if we don't truly understand their reasoning? It's the ultimate trade-off between efficiency and accountability. Thanks for joining me.